Hi, it's great to see you all again, and we get back to soil physical properties. And today I will go over on soil density, porosity, water, and aeration. First of all, we look into density. Before we get into the soil density, I like to show you guys with the relationship between mass and volume of the soil itself. So from the figure here, you can see that based on the soil we have here, this is a whole aggregate of the soil that you have, and then trying to imagine that you will have mass and volume relevant to air phase, water phase, and solid phase. So you can see that the total volume of such a soil equal to volume of air phase plus volume of water phase, where actually it's gonna be a liquid phase, but most of the liquid in soil system is water, and that's why we got the subscript W here in that case, plus the volume of the solid phase is basically all the particles in organic or organic matters that involved here. And we have mass relationship here showing you that the total volume M with the subscript T equal to mass of air plus mass of water and mass of the solid. So please keep in mind that we have to imagine that all these mass and volume is separately, but in the real situation they together. But in terms of some of the parameters that I'm going to show you next, which is the density, you have to keep in mind that that is totally based on the mass and volume relationship here. First, we start with the soil density. Here, I have two different kinds of density. First one is specific density or particle density. You can see from the formula here. Here we call the symbol is rho. Rho subscript S, or basically the density. Rho is a symbol of density. The subscript S stands for the solid phase. So specific density is the ratio between the mass of the solid phase divided by the volume of such a mass. Mass of the sorry, get back to the question one more time again. I'm just confused myself. Sorry. So we have the rho S as a specific density equal to mass of the solid phase divided by the volume of the solid phase itself. Okay, ms divided by vs, and that will give you actually it can be any number actually, but in general, as far as the soil component could be, there's a report showing the number will be in a range of 2.5 to 2.8 megagram per cubic meter, or in the unit of gram per cubic centimeter. Or you can say that average for the whole range will be 2.65 megagram per cubic meter, or 2,650 kilogram per cubic meter. So you have to make sure that you understand all different units here. But this is a kilogram per cubic meter. This is the SI unit. So that's why I highlight it out in red color. So we have specific density based on the volume of the solid phase. Now take a look here. Below here we have rho B, where B stands for bulk density. This is bulk density, equal to the mass of solid phase, again the same up here, but then divided by the total volume. Now as you remember that the total volume, let me get back here one more time. So for the particle density, we're actually focusing only on the solid phase. So it's only the volume of the solid part, that's it. But for the bulk density, we focus on all of volume of the soil. So that includes the volumetric of air and also the water. So when we like to make a comparison between rho B and rho S in one soil, you will see that it's totally general that particle density will be larger than bulk density in the same soil. So you can see the range for typical soils for bulk density will be 0.8 to 1.8 megagram per cubic meter, or 0.8 to 1.8 gram per cubic centimeter, or this is going to be 800 to 1800 kilogram per cubic meter. So you have to play around with the all different units here. So up to this point, let me share some idea here. You see that we have a really typical number for specific density, which is 2.65 or 2650 kilogram per cubic meter. This is a really typical average number that we always use. Well, turns out this is actually related to the minerals or mineralogy of the soil itself, where you see a lot of silicate mineral involved in the soil system, and that's why the where the average of this value come from. So normally we will see that the specific density for silicate mineral or silicon dioxide is about 2.6 to 2.7, and this is number is just right there in the middle. So that's the reason why you get this number. Whereas for bulk density, you will see that the number can get lower than 1. You see that this is 0.8 gram per cubic centimeter. I think you're probably familiar with that number, especially when you compare with water density. For water density, we have a rough idea that it's gonna be about 1 gram per cubic centimeter. I mean, in general, but well, actually, if you like to get the exact number, like the density equal to 1 gram per cubic centimeter, you have to measure right at 4 Celsius degree of water. That's the thing. But otherwise, in general, the number of density of water will be less than that, will be less than 1 in general. Okay, so you can see that this number was wrong. This is for soil. This is totally for soil, but you get the number lower than water. So imagine that you probably have the soil that kind of float on water surface, right? So we will discuss about that, like what kind of soil that can give you a really low number of the bulk density. You have to think about that. What makes that type of soil have such a low number for that? You can predict, or you can guess, from this formula as well, where you can see ms over vt. What caused the bulk density very low in terms of some specific type of soil. Yeah, I like to see your idea as well, where you can identify that type of soil in reality. So we keep that, and then we discuss more about that in the class as well. All right, we move to soil porosity. Porosity is a ratio that's showing us on the proportion between the volume of water together with air divided by the total volume. So this parameter basically telling us that how many proportion of the air and or water, or easily it's gonna be space basically. What is the proportion for the space within the soil system? So you can see that the number that you can get will be in the range of 0 to 1, and we have no unit, or we can call this is totally dimensionless number. But keep in mind that in terms of physics, you better know, even it's dimensionless, you better know that the first volume here, numerator, at the numerator you have the cubic meter, and denominator you also have the cubic meter as well, but this totally from different. Like this one below here, this is the total volume of the soil itself, and the one above here is the volume of just water and air. So you can see that even they come into the same unit, but then you have to think about in terms of physics or the meaning behind this formula. So from this range of number 0 to 1, it tells us that the soil porosity in one soil cannot uh, cannot have the value above 1. Basically, it's really true from the relationship over here, that you can see that you can have volume of water plus volume of air that go larger than the total volume, because total volume already include these two volumes, right? Together with the solid phase, which is really important for being soil system, that you're gonna have Vs no matter what. So that's why this ratio cannot go beyond 1. All right. However, if you can see down here, we have void ratio. The void ratio, on the other hand, have uh, the sum of uh, water volume and air volume divided by just the volume of the solid phase. And that's why I didn't put any range in here, because this number can go beyond 1, can go above 1 for real, especially when you have a lot of water in the soil system. See, this water ratio can go above that for sure, because the look at the denominator here, Vs is just a part of the total volume Vt. So you can see that you actually can see the relationship between epsilon here and E here. So that means the porosity and void ratio somehow can calculate, or can what should I say, can calculate from one to each other. Yep. And this is the beneficial relationship that I just said, that you can find like this one if you know the value of the bulk density and the particle density. Basically, you can find the porosity. It's pretty easy, and this is what we normally do for looking the porosity of the soil itself. You just measure the bulk density, and you know that in general, if you didn't have the soil that has really high amount of some sort of transition minerals, or sorry, transition elements, or gold element, something that really heavy that can cause you. Let me come back here one more time. See that the rho s can be some other value as well, not just like 2.65 here. In the case where you have uh, um, some sort of elements that have really high in atomic numbers, like the transition uh, uh, the transition elements, or gold elements, something like that, that can cause you a really heavy one, and that will give you the lowest will much more than this one, something like that. But otherwise, you can use this number in general for 2.65. So in that case, you already know rho s. You just measure for bulk density, and you good to go for porosity. And after you got porosity, you can get the void ratio almost right away via this function. All right. For soil bulk density and porosity, basically this is something that are affected by solid and pore spaces. When you have high pore space, so that means you intend to have low bulk density, and of course, because you increase the total volume. Remember, you have ms divided by Vt. Once you have bigger Vt, you tend to have lower bulk density. On the other hand, when you have low pore space, you have a higher value of the bulk density. In general, for fine texture soil like silt loam, clay, or clay loam, the number for bulk density will be range in between 1 to 1.6 gram per cubic centimeter. Now, if you like to change this unit to kilogram per cubic meter, you just times 1,000 here, right? So that will be 1,000 to 1,600 kilogram per cubic meter in the another unit. For sandy soils, this number will be range of 1.2 to 1.8 gram per cubic centimeter. Anyway, for the soil, even they have a lot of clay amount, clay size particle, but then they have a really good structure. like crumb or granular structure, they tend to have low bowel density as well. So that we gotta keep that in mind. And high organic matter will give you a very low bowel density. So this is probably the answer that why you can get the density lower than 1 gram per cubic centimeter. But you gotta tell the name for that type of soil that contain a lot of organic matter and cause the bowel density below 1 gram per cubic centimeter. Basically, just float on the water surface. The bowel density and porosity can help us to measure how compact or dense of the soil is. It totally relates on weight of the solid to the total volume, so that can explain about the ratio between pores and solids and everything. Bowel density generally just a weight of oven dry soil divided by soil volume. It's pretty easy to calculate that out. So basically, you just let me go back here real quick. Basically, you just make sure that you know the well-defined volume. That's why you have to use the core sampling that you already know the volume of the whole container. And once you do the core sampling to get the soil sample, you already have your soil in the shape of let's say cylinder. So basically, you know well-defined volume for such a soil. And after you oven dry until the mass of the soil itself get into the consistent value, so that means that most of or all of water are already left the soil sample. So then you will have the mass of the dry soil sample, and you just use that number divided by the total volume of your core. So you have to make sure that you use the core sampling wisely to get all the soil sample, just exact volume of your container itself. So that why you will get really precise number for bulk density. A little note here that bowel density increase, basically soil strength increase as well. Bowel density increased, you will get pore space decrease because everything kind of packed, and that's why you still have a lot of the mass of the solid phase, but then you have lower your volume. That's why you have the number of the bowel density increase. Please note that bowel density is related to the amount of pores in the soils as well. Relationship between soil bowel density and porosity, this is really important, and I'm pretty sure that you should be able to calculate that out. Like bowel density, how come you not knowing the porosity? So make sure that you understand how to use the equation. It's pretty straightforward, and then after you have all the number you need, you can calculate that out real quick. Alright, that's all for density and porosity. Now we move to soil water, which is really important part for soil physical property as well. For soil water, we have three relationship here showing you that for volumetric water content, see that we got theta V, theta subscript V. Theta V equal to the volume of water divided by the volume of the total volume of the soil itself. And this is again the same reason where you can't have this ratio cannot go beyond 1. All right, but this one actually can go beyond 1. Let me fix that real quick here. I gotta quick that out. Okay, it should be erased somehow. Alright, oops, okay, let me go back here again one more time. Go to the slideshow one more time so that we won't miss it again. And I'll move my window down here real quick. Okay, in terms of the gravimetric water content, or this is the by mass basically of the water itself. So the relationship based on the mass of water divided by the mass of solid phase. So with that case, you actually can have the mass of water that's go beyond the mass of the soil sample itself. So with that, definition, you can have zeta g that above 1 for sure. So it could be any number according to that meaning. And the last relationship here again is showing you the ratio between the volume of the water divided by the volume of water plus volume of air. This is somehow showing that, okay, the volume of water plus the volume of air representing the whole space that you can have, you know, like you have the total volume subtract with the solid uh, phase or volume of the solid particle. That's all. So that why you have just the space left, and that is the summation of volume of water and air. With that space, uh, what is the proportion of water in terms of volume unit in there? And that we call the degree of saturation. So with this number, you can see that you can have the capital S that go beyond 1 at all, right? Because the V subscript W or VW here is just a part of this denominator. You see that? So with this case, you can see that capital S is always, less or equal to 1. That's it. And once you have all the pore space occupied by water, so that means you have no longer have a space for the air anymore. And that's why this term become 0, approaching 0. And that will give you, in terms of numerator here is VW the same, but the denominator here, you will get VW as well, because VA here approaching 0. And that's why you give VW by VW that approaching 1 value for that case, and that is the saturated condition. Okay, we also have some sort of beneficial relationship in terms of water as well. First of all, in general, if you like to compare in terms of how to measure gravimetric water content or volumetric water content, well, actually the easiest way is just to measure the different weight between moist soil sample and dry soil sample. What I'm trying to say is zeta G is much more easy than the zeta V to measure in one soil. And that's why once you know zeta G, you can plug into this equation with knowing bulk density and water density, you can translate all these parameters to zeta V. It's pretty quick. The second relationship is the water in the unit of the depth. And here you can see that LW is equal to depth of water. And you just, really simple, just multiply your zeta V after you have from this relation times the depth of the soil that you're looking for. So you end up with knowing the amount of the water in the soil in the unit of the depth of water. Now, why we want to have the water in a unit of depth? And that's totally because you probably heard about when somebody said about the precipitation in general, like in Thailand, the average annual precipitation is about 1500 millimeter. See that? We always say it in the unit of the depth. So you can compare, because most of people do the irrigation based on the water unit of the depth. Of course, maybe millimeter or meter. Like in one season of growing a paddy rice field in one dry, you have to use at least a meter depth of water, flooding the whole area of one dry, something like that. Now, how to measure the soil water? We have more than just two methods, but I trying to categorize in the easiest way to think about the way to measure soil water. First of all, we call it direct method, which is the gravimetric method, and it's pretty easy, just like this figure showing you that you just weigh the soil sample when it's moist and when it's dry. I mean, completely dry, oven dry, so you have no water left at all. So with that, you can see that you this one is kind of I gotta do something here again. Okay, let's check here. See that? There is something wrong here. This supposed to be moist weight, right? Yep. And this supposed to be dry weight. I fixed that already. It's good to have you all see together. I made a mistake and I fixed it, and I'll explain more here. Let me save real quick. All right, and then I get back to slideshow again, so you all can see larger screen here. All right, I'll move my screen up a little bit here. Okay, that's good. So yeah, like I said, this is it's completely wrong. So you can see that by the definition, if you remember, in terms of zeta g, you have our mass of water, mw divided by ms, which is the dry soil sample. So of course the w1 here is dry weight of soil sample after oven dry at 105 Celsius degree, and w2 here is a moist weight of the soil sample. If you subtract the difference between W2 and W1 here will give you the mass of the water, of course, divided by the dry mass of the soil sample times 100. You can get a percentage of the water content. Because normally this number is this ratio generally is it could be lower than 1 in general, but for zeta g itself, if you remember that the number can go beyond 1 as well, but the number is still pretty low unless you you multiply by 100, then you can see the bigger numbers. Second is the indirect method, which is use some other properties of the water itself to measure water. Like here, I'm showing you 3 different methods. First of all, porous block using the electrical conductance, neutron probe using fast and slow neutron, where you have like you just throw a bunch of fast neutron into the soil, and that neutron somehow hit the water molecule, and once it hit each other, it start transferring the energy, and that make the fast neutron to become slow neutron, and then you count back how what is the proportion between fast and slow, and then you can calculate back to the molecule of water that the neutron probe can detect in one soil system. And the last one is in the red color, of course, time domain reflectometry, or TDR. This is totally widely used because neutron probe here is give you really fast information, but at the same time neutron is somehow put you into a risky moment, and it's caused some sort of bad issue for your health. So time TDR, or time domain reflectometry, nowadays is really widely used, and people enjoy using it and get a lot of information about soil water history of the soil system for the most. All right, let me explain a little bit more in terms of indirect method, like that I didn't explain that much in terms of porous block that you use the electrical conductance. You can do some sort of calibrate from the dry condition to the wet condition, and then you will get electrical conductance different. If you have dry soil, you have low electrical conductance, and when the soil get wet, you will have high electrical conductance. So that means with the calibration curve there, you can change from electrical conductance to a water content, basically. But again, for time domain reflectometry, or TDR, this is totally widely used, and in terms of a technique, they actually use electromagnetic wave, which is just the light, the light from the sun. This is a really good example for electromagnetic wave. Is something like that going to detect one of the one of the water property, and that's its dielectric constant. This is constant value. that you can check. Let me explain a little bit about dielectric constant. If you remember the water molecule where you can have oxygen and hydrogen, and turns out electrons spend more time in the oxygen atom, and that gives you kind of negative polar, right? Negative polar there, and then have positive polar in hydrogen spot. So with that, you can see that even electrons spend much more time in oxygen, but sometimes it's kind of come down and spend some time with hydrogen. Once electron move back and forth between these two atoms, it gives you such a electric from one polar to another polar, and that kind of constant in water molecules. So with that knowing, you can identify, because the free water, this number will be around 80. The dielectric constant will be 80. For soil mineral will be range between 3 to 5, and soil air will be equal to 1. So with the by definition, from dry soil to wet soil, you will have the number of dielectric constant will be various. So that's why you can calibrate for getting information of soil water based on the electrical signal you get. And this is somehow it look like this is really prototype, but just like to show you that this is how we plug in the TDR probe into the soil here. See that, and then you can read the number here, and make sure that you have all the probe plugged into the soil. And the measurement unit will be in terms of volume unit, which is the zeta V that you will get. All right, let me see. Okay, let me stop right here, and then we come back to another clip, because I like to separate them, because I like to keep it short, so it's going to be a lot easier to listen to. Okay, we start again with the type of soil water, but with the clips. Thank you so much for watching, and I hope you guys get the information about soil physical property based on density, porosity, and some part of the soil water. We come back here with these slides again in the next clip. See you guys. Bye bye.